So today we're going to look at Taylor polynomials and how they help us, how they're approximations to a function. So yesterday we learned how to expand a Taylor polynomial and a Maclaurin polynomial, and which is a Taylor polynomial centered around x equals 0, so c is equal to 0. What we also learned was that we have a couple power series that we need to memorize. So e to the x expands to 1 plus x squared over 2 factorial, so on and so forth. The nth term can be described by x to the n over n factorial, which means that we can write this as a summation of n is equal to 0, the sum from n equals 0 to infinity of x to the n over n factorial. Then we have the sine of x, which I remember as sine is an odd function. So you use odd powers. We used odd powers here. Okay. And then the number underneath matches. We always start with a positive term and then go negative. Okay, so x and then x minus x cubed plus x to the fifth, so on and so forth. The nth term can be written as negative 1 to the n times x to the 2n plus 1, and then in the denominator, 2n plus 1 factorial. Okay. And lastly, we have, and then we can write, so therefore we can write the polynomial as the sum from n is equal to 0 to infinity of the nth term. Okay. Lastly, we have cosine of x. Cosine is an even function, so we always have even powers. Its nth term rule is negative 1 to the n, x to the 2n over 2n factorial. And we can add the sum of the terms from n equals 0 to infinity of the nth term of the series. Okay, so first we're going to find the third degree Maclaurin polynomial. So again, Maclaurin means that we are centering around c is equal to 0, and we want to say the third term. So we're going to end up writing to the four terms here because we want to do the third degree, not third term. Okay, so I would say the polynomial, I can say f of x is about equal to the polynomial of x, or p sub 4 of x, right? And, 3, because it's the third degree, and that is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So this polynomial helps us estimate the value of e to the x, okay, when we're centered around 0. And so what we can do is use the polynomial in place of the function to evaluate, as long as it's a good representation of the function. So we're going to use the answer to A to evaluate the limit as x goes to 0 of f of x minus 1. F of x, remember, is e to the x. So basically what we're doing is the limit as x approaches 0 of e to the x minus 1 over 2x. And what we end up with is e to the 0 minus 1 over 2 times 0, which is 1 minus 1 is 0 over 0, which is an indeterminate. So we could apply L'Hopital here, which is totally legit. But what we want to do is find the answer using our Taylor polynomial. So instead of e to the x, I am going to replace it with our approximation, the polynomial of x. Okay, so I'm going to write the limit as x approaches 0 of 1 plus x squared over 2 factorial plus x cubed over 3 factorial minus 1 over 2x. And what happens is the the ones cancel, okay? And I get the limit as x approaches 0 of, and I'm going to go ahead and multiply this fraction now by the denominator of 1 over 2x, okay? So x over 1 over 2x would be 1/2, and then x squared over 2 factorial over 1 times 2x would give me plus 1. One of the x's cancel, so I get x over 2 times 2 factorial plus x squared over 2 times 3 factorial. And so anything, when I plug in my 0, I just get 0, right? 0 divided by anything is 0. So these are going to go ahead and cancel. So what I end up with is the limit is equal to 1/2. Okay, so if I had applied L'Hopital back here, let's just verify that this is all true, the limit, or that it all works with each other. Let's take the derivative of the numerator. The derivative of e to the x minus 1 is e to the x, and the derivative of 2x is 2. I'll go ahead and direct substitute in e to the 0 over 2 gives me 1 over 2. Matchy, matchy. Yeah. All right. So the next one. Suppose that the function f of x is approximated near x equals 0 by the third degree polynomial, Taylor polynomial, p sub 3 of x is equal to 2 minus 5x squared plus x cubed. So first off, I wrote these things in the wrong place. Okay, so what we want to do is find the value of f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. So remember that the polynomial is always set up the same way. So we have the first term is just f of c, the value you're centered around. And then the second term is equal to f prime of c times x minus c. The third is f double prime of c, so on and so forth, okay? So what I want to do is just look at the p sub 3 of x, and what I know is that the first degree, the 0 degree term, 2 is equal to f of c. So f of c, with c being 0, because we're centered around x equals 0, so I can write f of 0 is equal to 2. It's basically the first term, okay? The second term, f prime of 0 is equal to the derivative. It is equal to the derivative of the first degree term, okay? So not the derivative of the first degree term. It's equal to, we have to do some calculations, but we find it by looking at the first degree term. So I notice that there is no first degree term, so f prime of 0 is equal to 0. That's it. Okay, let's do f double prime. This one is a little different. I'm going to look at my x squared term. Okay, so I'm going to take my x squared term, 5x squared, and I know that the way I get 5x squared when I expand out my polynomial is that I take the second derivative centered around 0, because we're centered at c is equal to 0, and I multiply that by x minus c squared, so x squared, over 2 factorial. Now to find the second derivative, I just need to isolate f double prime of 0. So what happens is I'm going to divide both sides by x squared. That's convenient because it cancels out that x squared, and I get -5 is equal to f double prime of 0 over 2 factorial. So I will now multiply by 2 factorial, which is just times 2. Okay, so I get -10 is equal to f double prime of 0. So we're breaking down the structure of the polynomial to pick out the derivatives. Okay, the third derivative, f triple prime of 0, we got to refer back to the x cubed term. So I can write 8x cubed is equal to, I get that term by multiplying the third derivative at 0 multiplied by x minus c cubed, and our c is 0, over 3 factorial. So we know that the cubes are going to cancel. So I need to multiply both sides by 3 factorial, which is 6, okay? So I end up with 6 times 8 is 48, which gives me f triple prime of 0. Okay, so just picking out, matching up, doing a little algebra to solve for our first, second, and third derivatives. Okay, so now, does f have a local minimum, a local maximum, said those backwards, or neither at x equals 0? And we need to justify our answer. So at x equals 0. So what I remember is that f prime of 0 is equal to 0. So I can use my first derivative test. So the problem here is that this is a critical number. So when I set up my number line at x equals 0, we have a 0. Our values are not going to be positive or negative. So I don't know. I can't use the first derivative test. So we use the second derivative test. Okay, and for the second derivative test, what we end up with is we need f prime of x to equal f prime of a, which our a or c is equal to 0. So condition number 1 is good. So the second thing we do is we test the concavity. So we need the second derivative to tell us if our function is concave up, concave down, or inconclusive. We will look then at the second derivative. So my second derivative, f double prime of 0, is equal to negative 10, which is less than 0. So that means my function is concave down. And so that also means that f has a local or relative max at x is equal to 0. Okay, so because we have these two conditions, that the first derivative is equal to 0 and that the second derivative is less than 0, we know we're going to have a local max or a relative max at x equals 0. All right, so we're going to find the next example says to find the 6th degree polynomial, Maclaurin polynomial, for f of x is equal to cosine x. Okay, so if you didn't memorize these, Maclaurin means, one, that your function is centered around x equals 0. So we put c is equal to 0. Okay. And if you didn't memorize this, what we need to do is remember to take a lot of derivatives. So I start with f of x is equal to the cosine of x. The first derivative of that would be negative sine x. The second derivative of cosine x is negative cosine x. The third derivative of cosine x is sine x. And then we repeat. So I have f of 0 is equal to 1. F prime of 0 is equal to 0. F double prime, of 0 is equal to negative 1. And F triple prime of 0 is equal to 0. So all of when I set this up, all of the, let's see, this is the degree 0, degree 1, degree 2, degree 3. So all of the odd degrees are going to cancel out. So I'm going to write the polynomial p sub 6 of x, because it's the 6th degree, is equal to 1. Remember, it's f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus it continues to f to the 6th derivative of 0 times x to the 6 over 6 factorial. So let's go ahead and write that out. So I have p sub 6 of x is equal to f of 0 is 1. My first degree is going to cancel because of my 0, f prime of 0 is equal to 0. Then the next factor, f double prime of 0 is negative 1. So I'm going to put minus 1 times x squared over 2 factorial. The third degree term will cancel. The fourth degree term will end up kicking back up to positive 1. So plus x to the 4th over 4 factorial minus the 5th degree cancels, and the 6th is minus x to the 6th over 6 factorial. That is our 6th degree polynomial, Maclaurin polynomial of cosine of x. Remember, if you memorized these, then you can just write it out. You don't have to do the derivative thing and plug in the 0 and do all that business. Okay? All right. Another thing to remember about a cosine, the polynomial for the cosine function is that I just think cosine is an even function, so we use all even degrees in a cosine function. Okay, so the next part is we're going to use our answer in A, so our polynomial here, to approximate the value of the integral from 0 to 1 of 1 minus the cosine of t over t squared dt, so that the error in the approximation is less than 1 over 500. Okay, here we go. So instead of cosine, this is too difficult right here. This is too difficult to integrate. So we're going to use p sub 6 of, we're going to use p of t to integrate. Okay, so the polynomial that approximates cosine. So we have the integral from 0 to 1 of 1 minus, and instead of cosine t, we're going to plug in our polynomial because we can do that. 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial minus t to the 6th over 6 factorial. Okay, and I had to use a very specific number because, you know, planned it that way. Okay, so we go ahead and I'm going to go ahead and subtract this 1 minus 1, and I'm going to also change all my signs. So I have the integral from 0 to 1 of positive t squared over 2 factorial minus t to the 4th over 4 factorial plus t to the 6th over 6 factorial. And then I'm dividing that all by t squared dt. Okay, I'm going to go ahead and move this t squared to the numerator by multiplying by 1 over t squared. And that cancels the numerator. And then in the denominator, it cancels the denominator. And in the numerator, I get, let's see, t squared divided by t squared is 1. So I get 1 over 2 factorial minus t squared over 4 factorial plus t to the 4th over 6 factorial dt. Okay. Remember, factorials are just a value. It's like actually a constant value. So it's not as scary as we think it's going to be. Okay. So when I take the integral, I just need to raise the power. So this is 1 over 2 factorial is just 1 over 2 times t minus, remember we're raising the degree to the third degree, so I get 3 times 4 factorial, okay, plus t to the fifth over 5 times 6 factorial, evaluated from 0 to 1. Okay. All right, so let's go ahead and substitute in the 1. So I get 1/2 times 1 minus 1 cubed is 1 over 4 factorial is equal to 24. So 3 times 24 is 72. Plus, I'm substituting in the 1. I get 1 over 5 times 6 factorial. So 5 times 720. And then minus 0, because all those zeros are going to just make a 0. Okay. So this is I'm just going to rewrite it. This is the answer. 1 minus 2 minus 1 over 72 plus 1 over 5 times 720. And what it's asking is we want to write the polynomial so that it says 2 approximate the value of the integral so that the error in your approximation is less than 1 over 500. So I just look at the terms, and I first need to make sure that there's some alternating action here, because all we know how to deal with is alternating errors. So what I can tell you is that since the terms are 3 things, alternating, remember we need some of that those negative values to offset the positive values. So it's alternating, decreasing in magnitude, the absolute values are decreasing, and the limit approaches 0. Then we can use our error analysis, our alternating error analysis. So we know that the absolute value of the error has to be less than 1 over 5,000, 5 times 720. So, and that is less than 1 over 500. So we're looking for the error, the first term, that will give us an error that is less than 1 over 500. So when I look at these terms, I'm like, 1 over 72 is not less than 1 over 500. But 1 over 5 times 720 is less than 1 over 500. So that is our error. So our error is less than this value. Okay, so we're good there. Okay, it's already smaller than 1 over 500. So we're good. Okay, so our answer is, back to our answer, we don't want this term because it is already less than 1 over 500. So I only need to add up the first two terms. So I need to add 1 over 2 minus 1 over 72, which gives me 35 over 72. So this is an approximation. So I can say that the integral, let's just put it, from 0 to 1 of 1 minus the cosine of t over t squared is about equal to 1/2 minus 1 over 72. And that value, when we add it together, is 35 over 72. And there is a small error. It's approximation, but it's pretty stinking close. Okay, so in fact, let's use our calculator to calculate out the error. So I went ahead and used my Math 9, plugged in my function here, okay, and I evaluated this, and I got the approximation is equal to 35 over 72, which is equal to 0.486. So that's this, okay? And then in the calculator, I got the actual value, which is the integral from 0 to 1 of 1 minus the cosine of t over t squared dt. Whew. And that equals 0.486. Whoa. I subtracted those and I got an error of, okay, so to get the error, I did the actual value minus the approximation. Okay, so I did the integral minus the fraction, the 35 over 72, and I got the value of 0.000274. So this is how much our approximation is off by. Whoa, pretty cool, huh? Yeah. All right, that's it for today.